Kamnitzer from University of Toronto, who will speak about categorical G-actions for modules over truncated shifted Yangians. Please.
Okay, thank you very much for the introduction and the invitation to speak. So let me begin by discussing about affine Grassmannian slices. Please let me know if you have trouble reading. I hope it should be clear. Oops. Grassmannian slices. So what are these? We have G, a semi-simple group. And now we're going to be studying in the affine Grassmannian of G, which means we take G over the Laurent series and divide by G over power series. So it's an infinite dimensional projective variety that's kind of like a flag variety for an affine Kac-Moody group. Inside this affine Grassmannian, we're interested in the orbits of this group here. So we call it Gur lambda. So we take this G over power series and take its orbit through a point T lambda. And in order to get all the orbits of this group, this G of O group, we need only to take lambda here to be dominant coet. So here, lambda is a coet, so it defines a map from C star into the maximal torus of G. And therefore, a point of this maximal torus, or a point of G over the ring of functions on C star, so that's polynomials in T and T inverse, and therefore a point in the affine Grassmannian. So that's the meaning of this notation T lambda. So T lambda is the resulting element here, or the resulting element in the affine Grassmannian. And these orbits here, they partition the affine Grassmannian. Okay. One other point, it's not that important for the talk, but maybe interesting, is that the affine Grassmannian has a modular interpretation in terms of principal G bundles on P1, which are trivialized away from the point 0. And this space here corresponds to those principal G bundles which satisfy a pole condition at 0. The trivialization, rather, satisfies a pole condition at 0. So yeah, let me write something which I didn't say, which is, sorry. Wait, I'll just write. The affine Grassmannian is partitioned into these orbits over all these dominant coets. Okay. And now we're interested in transversal orbits to these orbits. So for these transversal orbits, we will take a different group, which is the group G1 T inverse. So here we take G of T inverse. So this is embedded inside of the Laurent series, polynomials in T inverse. And this G1 refers to those things which, when we evaluate T inverse is 0, become the identity element in G. So I take the orbit of this group through a similar point T mu, and that thing is denoted W mu. And these are transverse to these Gur lambdas that I discussed earlier. And then we can intersect these two systems of transverse orbits to define W lambda mu's. So here again, mu is dominant. And then now we define our main object of study, this affine Grassmannian slice, to be the intersection, well, rather of the closure of one orbit intersecting the other orbit. So we like to, you can kind of picture this affine Grassmannian orbit, these affine Grassmannian orbits, these Gur lambdas. Here's maybe a lambda, here's Gur lambda. There's a kind of sphere or something, and then maybe here I have a point mu, and here I have on the outside here, like this will be W mu. And so this intersection is like the stuff trapped in between. Kind of funny cartoon. Okay, so that's the definition of this W lambda mu. So this is what we would call affine Grassmannian slice. And again, it has a modular interpretation. So it's a moduli space of principal G bundles. I'll write it sort of out a little bit. Principal G bundles. P on P1 with trivialization I away from 0. Then now where the lambda and mu come in, the lambda and mu come in such that when phi has poles somehow less than or equal to lambda. So I won't explain in what way the poles can be less than or equal to lambda, but it's possible to give an interpretation of that. And the second condition is that the isomorphism type of the bundle is given by mu. Isomorphism classes of principal G bundles are labeled by dominant, on P1, are labeled by dominant coeds. And the isomorphism type of the bundle we want to be mu. And then there's plus a condition, a minor detail, which is that there's also a condition in infinity, which somehow is related to the fact that we took this group G1 and not just the G of CT inverse. Okay, so these are affine Grassmannian slices. So the definition may look a little random if you haven't studied them before, if you're not familiar with affine Grassmannian. So now I'd like to explain what are some reasons why we're interested in them. Okay, so here are some beautiful properties of affine Grassmannian slices. So, one. First of all, what kind of structure do they have? Well, they're finite dimensional Poisson varieties. Poisson varieties of sort of the best kind. They have symplectic singularities. So they have, in particular, finally many symplectic leaves. And they sometimes admit a symplectic resolution. Essentially, whenever lambda is a sum of minuscule weights, and some other boundary cases. But essentially, they admit a symplectic resolution when lambda is, if and only if lambda is a sum of minuscule weights.
So I'm a bit confused. So where they are symplectic resolution, they are symplectic singularities, so these symplectic leaves, they have different dimensions, or what?
So having symplectic singularities means that there's it means that there is a resolution on which the Poisson structure extends to a 2 form on the resolution, but not necessarily non-degenerate 2 form. And separately, they do have symplectic leaves. The symplectic leaves are simply the smaller, it's easy to write the definition. So recall that this thing was the intersection, lambda bar, intersect W mu. And of course you could, well, this lambda bar itself is the union of smaller nus, where nu is smaller than lambda. And if we want to have non-zero intersection with mu, then it should also be bigger than mu. And so the symplectic leaves are simply these intersections. So those are the symplectic leaves.
Without closure, yeah?
Yeah, so now without closure. Okay. So they have some nice structure in that way. Another nice thing about them is they admit quantizations. So quantization, so they're affine Poisson varieties. So in particular, their coordinate rings are Poisson algebras. So by a quantization, I mean filtered non-commutative algebra whose associated graded is isomorphic to the coordinate ring. They emit quantizations, y lambda mu. They're called truncated shifted Yangians. And as the name sort of implies, they're subalgebras of, they're sorry, subquotients of the Yangian. So they have a explicit description by generators and relations.
So what kind of Yangian do you mean? Your group G is kind of very general.
Yeah, the Yangian of G, and it's with its Drinfeld Yangian of G. And it's with its Drinfeld presentation. Okay. So the third reason why they're nice, and maybe somehow the principal reason why I'm interested in them, is that they give geometric incarnations of representations of G, or more precisely of its Langland's dual group, or Langland's dual the algebra G. So what I mean by this is that the intersection homology, using the geometric Satake correspondence, the intersection homology of such a affine Grassmannian slice is isomorphic to a weight space in an irreducible representation. So here, recall that lambda was a dominant co-weight for our group G. So by the definition of the Langland's duality, this lambda is now a dominant weight for the algebra G check. So I have an irreducible representation V lambda of G check. This is my notation V lambda for the irreducible representation of the highest weight lambda, and V lambda of mu means the mu weight space in that irreducible representation. And so this gives a weight space in that irreducible representation. And to be a little bit more precise, I don't really want intersection homology here. What I really need is the hyperbolic stock of the intersection cohomology sheaf. But those two things have, anyway, the same dimension. But technically, this is actually the associated graded of this. Okay. So this, again, is a byproduct of the geometric Satake correspondence. Here's another important property or fact about them. Maybe I should have said this right at the beginning of this section, but okay, I'll say this. Maybe I'll just say it now. That these affine Grassmannian slices and these properties that are mentioned, they were studied and introduced by, well, principally by the following people: Braverman-Finkelberg. I guess Braverman-Finkelberg were really the first to study them. Then later, some of what I'm mentioning is joint with them in Nakajima. And then also myself, and also some of my co-authors, like Alex Weeks, Ben Webster, and Oded Jacobi. So these are people who these different properties are, study these different properties. Okay, now I'm number 4. Just like now number 4 is that this W lambda mu is a Coulomb branch. I'll explain a little later in my talk what this means to be a Coulomb branch, but I think you had Nakajima speaking here not too long ago, so you already heard something about this. So W lambda mu is the Coulomb branch for a quiver gauge theory.
Again, so your G so far was general. What kind of quiver do you mean?
So G was any semi-simple group. So right. This resulting quiver will be the quiver related to the Dinkin diagram of that group. If that group is not simply laced, then you need an enhancement of this notion of Coulomb branch, which was developed by Nakajima and Weeks. So So in the non-simply laced case, this notion of Coulomb Branch, this enhanced notion was studied by Nakajima and Weeks. And this quiver gauge theory, the resulting Higgs branch, at least in the simply laced case, this Higgs branch is a Nakajima quiver variety. And I'll write, maybe just as a notation, like m lambda mu for that Nakajima quiver variety. So this is what Nakajima would usually write mVW, right? M lambda mu. Okay, so this is the basic properties of these affine Grassmannian slices, why we're interested in them. Then I'll say one more thing of a general nature, which is that I explained the definition of this affine Grassmannian slice. When I explained the definition of this, mu here always had to, both lambda and mu had to be dominant. The reason is, well, because that's what partitions this orbits in the affine Grassmannian. That's the indexes the orbits in the affine Grassmannian. But of course, for example, this property, you might reasonably ask what happens when mu is not dominant, since of course the right-hand side exists when mu is not dominant. And for various other reasons, it's nice to have these spaces when mu is not dominant. And in fact, they can also be defined when mu is not dominant, but it turns out their definition is somehow more complicated in the case when mu is not dominant. But it can be done, and all the same good properties hold, including this truncated shifted Yangians, these quantizations, although they're no longer subquotients of the Yangian. Any questions about these general properties of these guys?
Yeah, the property 2 seems to be kind of separate from the rest.
The fact that they admitted quantizations.
Yeah.
Well, I mean, property 2 is in some way a formal consequence of property 1, because there's a general theory of quantization of symplectic singularities, which says that such quantizations exist and are parameterized, are unique exist. There's a unique family of such quantizations. So in some sense, the existence of these quantizations is not a property. What I mean in some sense by property 2 is that we can actually explicitly write down these quantizations and relate them to the Yangians.
Yeah, that's what I mean, that you have some quantum group, but you do not mention how. I mean, it has its own representation theory, which probably correspond to the geometry of this.
Yeah, exactly. Yeah, so we'll get into that a little bit more in the talk. Okay. So before sort of going to the main problem that I want to discuss, I want to discuss a little bit more about these quiver varieties. Well, some facts, recall some facts about quiver varieties. Maybe I should have said at the origin that, so I said that there's that the quiver variety is the Higgs branch and of this quiver gauge theory, for which the affine Grassmannian slice is the Coulomb branch. And in this case, we say that the relationship between the two varieties is called symplectic duality, or some people say three-dimensional mirror symmetry. So this theory of symplectic duality is kind of a, well, relatively new topic, now maybe 10 years old. And people are very interested in understanding if there's some phenomenon on one side, some properties on one side of the symplectic dual, what do we see on the other side of symplectic dual? So what mostly I'm going to talk about is in some sense, some manifestation of that. So for that reason, I'm going to start talking a little bit about quiver varieties. So we have this quiver variety, m lambda mu, and one property that it has is that its top homology is isomorphic to that same weight space that I mentioned earlier of the weight space of the irreducible representation of G check. This again, now we're back in the simply laced case. Assuming G simply laced. And not only is its homology isomorphic to this thing, but in a kind of explicit way, in that Nakajima constructed an action of this G check on the direct sum of these top homologies of these varieties. And how does the action work? Well, it uses some correspondences look like this. So there's m lambda mu, there's m lambda mu plus alpha I, and then there's a correspondence, so some space which sits in here. And this correspondence is used to define a linear map from this top homology to this top homology, which realizes the action of the Chevalier generator. Or both the actions of the Chevalier generators EI and FI in G. So there's these guys, EI, FI, they'll be giving us linear maps back and forth between this H top M lambda mu and H top M lambda mu plus alpha. Okay, so there's some explicit correspondences here, which allow us to define these linear maps, and together, these EIs and FIs, they'll give us an action of G check. Maybe just to quickly demystify this in case in the case is not familiar to you already. For example, if we took G to be, squeeze in an example right here. If we took G to be SL2, then these quiver varieties would just be cotangent bundle of Grassmannian GKN, and this correspondence would involve the cotangent bundle of GKN and the cotangent bundle of GK plus 1n, and the correspondence would be the co-normal bundle of the natural correspondence, incidence correspondence between GKN and GK plus 1n. Okay, so this is the theory for quiver varieties. And not only is there this, well, nice description of the action of G check, but this can be categorified. So what does this mean? So there's these Nakajima quiver varieties are defined by Hamiltonian reduction, and there's a natural way to perform a quantum Hamiltonian reduction to obtain some quantization. So we have A lambda mu, I'll call it. So this is a quantization. Of the quiver variety defined by quantum Hamiltonian reduction. So it doesn't really have a explicit sort of description. Well, in some cases it does, but in general it doesn't really have an explicit description. It has kind of an implicit description by this procedure of quantum Hamiltonian reduction. But nonetheless, we can upgrade these correspondences that I mentioned, these linear maps coming from correspondences, to functors between categories of modules over these A lambda mu's. In particular, we can study what's called category O for A lambda mu. So this A lambda mu has a Z grading, and category O for A lambda mu, that's a category of modules compatible with Z gradings that are compatible with the Z grading in the algebra, but the Z grading should be bounded above. And then, so what I'm explaining now is in the work of Ben Webster. So he defined a categorical action. Categorical action. What does it mean, categorical action of G check? It means that we get functors EI and FI between these category O's. So we have functors from category O for lambda mu, category O for a lambda mu plus alpha I, called EI, and then a functor back called FI. And they satisfy categorification of the usual relations between in the Lie algebra G. And together this defines this categorical action of G check, and it categorifies this representation that we start with. Okay, so for the equivariety, somehow this is all well understood, and somehow the reason why it's well understood or why it works well is because of these correspondences are very natural. These correspondences I mentioned here. Well, I didn't describe them explicitly except in this case, but these correspondences are very natural and very easy to study.
So Joel, are these categories derived or just abelian?
Yeah, later not, but right here they would, yes, we would have to work. These functors are not exact functors. We would have to go between the corresponding derived categories, yes. Okay.
So, Joe, so those functors between modules over categories, so do they, well, say if G is SL2, is it a categorical geometric SL2 action in the sense of your papers about T-star Grassmannians?
It's sort of what in relation to my papers, it's like it's not really a category. It's not a categorical geometric SL2 action in the sense of my papers, but it's closely closely related to what we do in those papers, kind of quantization, well, like the same kind of thing, but on the level of these module categories. But it is an actual categorical G action in the sense of Kovan of Lauda and Ruquier.
Thank you.
Yeah, so in fact, that's kind of what I want to mention now. So another source of categorical G actions are these special algebras, which are kind of cooked up to have categorical G actions on their modules, called Kovan-Lauda-Ruquier algebras. Or there's a generalization called Kovan-Lauda-Ruquier-Webster algebras, KLRW algebras. And there's a close relation between this category O for A lambda mu that we were just talking about. This is related to this modules for one of these Kovan-Lauda-Ruquier algebras. So here this T lambda mu is a KLRW algebra. And this relation of this dotted line is not actually an equivalence of categories. It's actually a kind of causal duality between this category and this category. So there's graded versions of these, and then their derived categories are equivalent. So this is not really the main topic of my talk, so I'm not going to go into too much detail. But I'm just emphasizing this because we're going to see this algebra in a second. Okay, so now let's go back to our return now to our affine Grassmannian slices, W lambda mu, and their quantizations called truncated shifted Yangians, Y lambda mu. So because these guys are the symplectic dual to the equivarieties, and for other reasons, it's natural to try to relate category O for these truncated shifted Yangians also to these KLRW modules. And this is what we did. So a theorem we proved last year. So myself with Peter Tingley and Webster and Alex Weeks and other Jacobi. Is that there's an equivalence of abelian categories. So now actually abelian categories come in. between category O y lambda mu and this KLRW algebra for lambda mu. And this equivalence is proven strictly by, I mean, using like the generators and relations description. So it's proven just sometimes just using pure algebra. Although a kind of inspiration or part of the method comes from a general method which works for Coulomb branches. And somehow if you don't think of this thing as a Coulomb branch, related to Coulomb branch as a Coulomb branch algebra, you probably won't think about this equivalence. Okay. So I mentioned, so what's interesting about this theorem, I mentioned, well, there's many interesting things about this theorem. One special case, actually, I'll just mention this just to sort of demonstrate the power of this theorem. So one very special case is if we take lambda to be n omega 1, and if we take mu to be, sorry, well, I should tell you what g is. We take g to be pgln. We take lambda to be n times the first fundamental weight. We take mu to be 0, or equivalently the L1 factor. Then in this case, the affine Grassmannian slice is just the nilpotent cone in SLN or GLN or PGLN, whatever. And the y lambda mu is just the universal enveloping algebra of SLN specialized at a given central character. And well, even in this case, this theorem is new. Well, not quite this theorem because category O for this algebra is pretty straightforward, but there's a version of this theorem where we replace category O by a category of Gelfand-Setlin modules. And then we get a description for the category of Gelfand-Setlin modules for SLN. And for example, it wasn't known of the number of like simple Gelfand-Setlin modules for SLN before this, and this theorem solves that problem. So even in this very special case, the theorem is kind of useful.
So what kind of answer gives the right-hand side in this case?
Well, a priori, the right-hand side may be like completely useful. For example, for the problem I was just mentioning about simple modules, simple Gelfand-Setlin models. But this right-hand side, it's the number. I mean, it can be okay. As I mentioned a minute ago, or that this guy will categorify this irreducible representation of G check V lambda. And if I replace it with this Gelfand-Setlin modules, well, it won't categorify the irreducible representation, but it will categorify some other representation. And using that description, you can figure out how many simple modules there are. In any case, let me continue. So, using this equivalence here, we can make the following diagram. We have category O for y lambda mu. We have this equivalence of abelian categories with T lambda mu mod. There's natural functors going back and forth. Let me just go in one direction. Functor EI to T lambda mu plus alpha I mod. So this functor exists because of, I didn't define this T lambda mu, but it's a certain, actually defined diagrammatically. It's a algebra defined by certain diagrams modulo certain relations. Originally developed, well, the diagrammatic form is developed by Kovanov-Lauda. The non-diagrammatic one form was developed by Ruki, and some kind of generalization which is needed in this theorem is developed by Webster. But in any case, this algebra is cooked up so that there is functors like this. So we do have functors EI and FI back and forth. And then here we can put a category O for this y lambda mu plus alpha I, and again we have this equivalence. And we know we have these functors which give this categorical G action. So there must exist something which goes here, of course, because we have equivalences on top and bottom. But how can we give a description of this thing? What is this functor between these two category O's? So that's the problem what I want to address today. And maybe slightly more generally, how can we relate this algebras to these algebras, or even more, how can we relate this W lambda mu's to W lambda mu plus alpha i's? are there some natural relation between them? Okay, so that's sort of the main problem to be discussed today. Now, what relation might you expect? I mean, naively, you might expect some natural correspondences like the ones between the varieties, but there don't seem to be any natural correspondences like that. At least you don't find them as easily. Now, one inspiration for a relationship is that there's a special case. So I mentioned before that when G is equal to PGLN and lambda is N omega 1.
So Joel, I see your hand, but I do not see what I
sorry.
write.
There we go. So in this case, I mentioned mu equals 0, but even if we take any mu, which is smaller than this lambda, so it would correspond to a partition of n, then this W lambda mu is a slow-to-a slice, or more precisely, a slow-to-a slice intersect the nilpotent cone. So this S mu is a slow-to-a slice. And by the results of Gann and Ginsberg from maybe 20 years ago, these slow-to-a slices can be obtained by Hamiltonian reduction by a unipotent group. Hamiltonian reduction, but like not by a reductive group, like as with the varieties, but rather by a unipotent group. So this leads to like the following inspiration that something like this would be true for W lambda mu, and that's what we'll see now. So we define an action of GA, the additive group, on any W lambda mu by the formula, simple formula, that we just take some A, like a complex number A, acting on brackets G, so that's an element in the affine Grassmannian, which happens to be in my W lambda mu, and we get brackets, so this brackets denotes like the equivalence class and the quotient by the G of O. And we get the result of left multiplication by xi of A on G. So here, xi of A denotes the ith root subgroup, or the alpha I root subgroup. So it's in for GLN or for SLN or something, it looks like that matrix. So this is an action of GA, and this it's why you might say why GA, because well we want to act with something one-dimensional, because the dimension of W lambda mu is given by the pairing between lambda minus mu and rho. Twice the pairing between lambda minus mu and rho. Dimension of W lambda mu is twice rho lambda minus mu. So that if we change mu to mu plus alpha I, this number will go down by 2. So that's somehow the numerics for this theorem. So this is a theorem of myself. It's not yet on the archive, but coming soon. My student Koa Pham and Alex Weeks. Oops, I'm going to move the camera, otherwise let's see the theorem. Okay, the theorem is that this action is Hamiltonian. And there's a moment map. Which I'll call phi. I won't define it, but it's relatively natural map you can define. One. So part 2 is there's an isomorphism. I'll just write the isomorphism. So if I take the Hamiltonian reduction at the moment map level 1 by the action of this GA, So it's like a algebraic, like a hyperkähler reduction. So I take the complex, I take phi inverse of 1, and then I divide out by GA. So this guy is isomorphic to W lambda mu plus alpha I. So that gives that gives sort of the desired relation between W lambda mu and W lambda mu plus alpha I. And even a slightly stronger statement is we prove, which is that stronger statement is that if you just take the inverse image of the non-zero of C star under this moment map, it's actually isomorphic to this smaller slice W lambda mu plus alpha I cross the cotangent bundle of C star in such a way that the GA action is only on this factor. And so that when you end up doing this reduction, you get rid of this factor. And then moreover, we have the quantum version of this. So if we take the quantum Hamiltonian reduction of the same guy, not the same guy, sorry, the quantum Hamiltonian reduction of the quantization of this truncated shifted Yangian, and you might ask what I mean by this thing, by this guy. What I mean by it is the following. I mean, we form the quotient y lambda mu mod the left ideal generated by the moment map. Well, by the lift of the moment, by the quantum lift of the moment map. I'll just denote by the same thing. Phi minus 1. That's because level 1. And then I consider this thing as a left module for y lambda mu, and I take its endomorphisms. So that's what I mean by this quantum Hamiltonian reduction. This endomorphisms of this guy is isomorphic to y lambda mu plus alpha. Okay. And then there's also like a version of this statement, which is that if I take y lambda mu and I localize by the same guy, that will be isomorphic to y lambda mu plus alpha I tensor differential operators on C star. Okay. A slight caveat about this theorem. So we proved most of this theorem, but not actually. This part of this third part is still conjectural. So this thing this guy in the third part, it holds as written for in type A, but outside of type A, this is like a bit of a weaker form is only true, which I don't want to bother explaining
if you consider different I's simultaneously, like I and J, so what's happened with those equivalences? This is sort of a Coulomb Branch story. On the Higgs branch, you have, I don't know, this like break group actions like this Nakajima, equivalences, which you are still in PGLN, yeah? It's all for PGLN.
No, this theorem. Oh, this theorem is true for any G.
All right. So if I apply like first Hamiltonian reduction with respect to phi, then to phi j, is there anything interesting?
Well, let's. There is stuff interesting, but that's okay. We don't. I would say that's a subject of future study. Yeah. Yeah. So recall that my goal was to understand what these guys. So I wanted to relate these two algebras for the purpose of defining functors between their category O's, for the purpose of trying to understand, to try to relate it to this categorical action that I mentioned, these equivalences with this KLRW algebras. Unfortunately, this equivalence doesn't seem to be very compatible with category O. We don't know yet. We don't know if it's possible to use this equivalence to really define a functor between these category O's. So this theorem, I'm about to get to a different theorem, but this theorem is nice and geometric. So we have a, relatively straightforward action, relatively straightforward, straightforward statement here. And it's nice and geometric, but somehow doesn't seem to work that well with the non-commutative algebra. Doesn't seem to work that well with the quantizations. So now I'm going to explain a different relationship between these non-commutative algebras, which comes more from the Coulomb Branch framework, but it's more mysterious. Okay. Any other question before I erase this part? So to explain this other theorem, I'll need to give a little bit more background on what it means by Coulomb Branch and so on. So the real problem now is I have to change the name of my group, but hopefully you'll forgive me. So now I have a new group. Now I have G, a reductive group, and not the same group that I started with. The group I started with is now called GQ. Okay. And now I have V representation of G.
Sorry, what is Q?
Well, Q is it's going to denote the quiver, like the quiver of G. So that's why it's somehow, I think, Nakajima's notation, I think. Okay, so if I have this group G and I have this representation V, I can define the Higgs branch in a straightforward way of this pair. And the Higgs branch is nothing but I take the cotangent bundle of V and I take its reduction by G. So in other words, I take the inverse image of 0, and maybe I take, so phi here is a moment map. And I take the reduction, the quotient by G. Maybe I take a GIT quotient, maybe I take a projective GIT quotient. Anyway, different versions of it. Okay, now I'm going to explain the Coulomb branch. I do something totally different. So this definition is due to Braverman-Finkelberg-Nakajima from, well, almost 5 years ago now, based on a work in the physics literature. So first, I'll go straight to the non-commutative algebra, non-commutative version. So I'm going to call it AGV. So it's defined like as follows. So I start by studying space of maps. Give myself a little more space. So I start by studying the space of maps from a non-reduced curve, which is obtained by gluing 2 copies of the punctured disk over the formal disk. This guy is D cross union D cross over D, sometimes called the ravioli curve. Sorry, I wrote that wrong. D union D over D cross. Sometimes called the ravioli curve. So I take maps from that ravioli curve into the stack quotient V over G. What does the space of maps really mean? It really means I have a pair consisting of a principal G bundle on this non-reduced curve, which means basically just 2 principal G bundles on the disk glued together on the punctured disk. And so that's somehow the G part. And then in addition to this principal G bundle, I have a section of the associated V bundle. So that's what a map consists of. And then this space of maps, I take its homology, C star equivariant homology, defined in an appropriate way. C star here acts on the disk in the obvious way. And this homology has an algebra structure defined in a convolution way. So somehow related to the fact of gluing, a third kind of guy on top of this. So that's this Coulomb branch algebra. It's a CH algebra. CH bar algebra, where this CH bar is the C star covariant cohomology of a point. And then we can specialize it at h equals 0 or at h equals 1. If we specialize at h equals 0, I'll write A0 GV. And that's the specialization at 0. And this is a commutative algebra now. And the spec of this commutative algebra is the definition of the Coulomb branch, which I'll write MCGV. So that's the Coulomb branch. So usually this thing is called the Coulomb branch, and this guy's called, I don't know, the non-commutative Coulomb branch, or the Coulomb branch algebra. Okay, so again, so I mentioned that our affine Grassmannian slices are Coulomb branches. So now let me make that more precise. So again, GQ will denote the group from the beginning of the talk. So it has Q will be the quiver associated to its Dynkin diagram. So I mean the Dynkin diagram along with a choice of orientation. And I the vertices. And what this group G who's the one we'll use as the input to this Coulomb branch construction will be the product over I of some GLVIs. So product over vertices of a bunch of GLNs. And I should probably have said this before here. So again, I have this lambda and mu, and I use them to define these VIs by taking their difference and writing their difference as a sum of simple roots. And I'll also write lambda as a sum of fundamental weights to obtain some other numbers, W's. This is the usual notation from Nakajima varieties. So G is this product of GLVIs, and then the V, the other piece of data for a Coulomb branch, is reductive group and a representation. So here's my group. Now I need the representation. So the representation will be, well, it's familiar to those who know about Nakajima varieties, what you need to make the Nakajima variety. So you put HOMs between these vector spaces corresponding to this Dynkin diagram, to this orientation of the Dynkin diagram. So VI C J over all edges I to J in Q. And then also there's a framing part. See, probably, maybe you can't see this, but it doesn't matter too much. Over this framing part. Hopefully you can just barely see that. Okay, so that's the definition. And if you use these guys, then the theorem, well, in the commutative case, it was the theorem of Braverman-Finkelberg-Nakajima. In the non-commutative case, it's a theorem of them plus four other people, including myself in an appendix, is that this is a affine. So the Coulomb branch is the affine Grassmannian slice, and the algebra, Coulomb branch algebra, non-commutative algebra, is the truncated shifted Yangian. Okay, so this is what I meant when I said that affine Grassmannian slices are Coulomb branches. And now we're gonna so this is the end of this little interlude here. So now we want to relate, again, we want to relate y lambda mu and y lambda mu plus alpha I. But I'm going to do something far more general about, discuss something much more general about relating different Coulomb branch algebras. So G and V again are arbitrary. Reductive group and representation. Not necessarily product of GLNs. Okay, another piece of data I'm going to need though now is a co-weight of G. So map from C star into G, or into the maximal torus of G. So co-weight. And then I'm going to look at another group, which is called L gamma, which will be the centralizer of the image of gamma. So that's some Levy subgroup inside of G. Contains the maximal torus of G because this guy maps into the torus. And then we'll also be interested in reducing this, making this representation. So then I made the group smaller. Now I'm going to make the representation smaller. So V gamma, this will just be the invariance in the representation for this action of C star. So Gx on the representation, and via gamma, C star x on the representation, and I take its invariance. And now L gamma will, because L gamma centralizes gamma C star, L gamma will act on V gamma. So I'm going to be interested in relating the Coulomb branch for GV and the Coulomb branch for L gamma V gamma. And they have slightly complicated relationship, but one that can be studied. While I'm doing this erasing, you can continue to see the definition of those guys. I'll leave it up there for a second, a little longer. Okay, so in order to relate these guys, we defined first of all a certain matrix algebra. So I won't get into its definition right now, but there's a way to define, I'll call it A L gamma GV. So it's almost the same as AGV. It's a matrix algebra over GV. So it's Morita equivalent over GV. Okay. And then we have the following theorem. So this is from a paper which is not yet on the archive, but it's slightly less far along than the last one I mentioned, but probably will be completed in the next couple of months. So first of all, there's an inclusion. From this ALV, okay, so we have going to be a few players. Now ALV is L gamma V. So again, I change the group, but I leave the representation alone. And this guy will include into this matrix algebra. And second, there's an isomorphism between the guy we're really interested in, L gamma V gamma, and a localization of AL gamma V. There's some particular element which we can study easily, and if we invert it, we get an isomorphism. So this leads to what we call a restriction functor. So we go from A modules for AGV, the original algebra. So we use the Morita equivalence. So this first step is very straightforward, at least from a categorical perspective. The second step, we restrict our module using this equivalence. And in the third step, we use this localization. Localize our module. And overall, this defines a functor. And this functor actually does have very good properties on category O. This paste this in category O. So for any G and B. Okay. So now to return to the, I'm almost done because I'm almost out of time here. So to return to the previous topic, or to the main goal of the talk. So if we take back to this G to being the product of GL VIs, and V being this direct sum of this blah blah blahs. If we're going to take gamma to be the first fundamental weight inside the ith VI. Okay, so that means I just map C star into the ith copy of VI into the top left corner. Then in this case, the corresponding L gamma, if you check it out, what will be the centralizer? It's pretty straightforward. It's just C star cross the product of GL VJ primes. And what's VJ prime? Well, it's almost the same as VI. It's VI if J is not I, and it's VI minus 1 if J equals I. So I just reduced the ith guy by 1, which is what I wanted to do, because that leads to y lambda mu plus alpha I. So in particular, the A of, and you can do a similar calculation on the V. For lack of time, we may not do it, but you can see that the A of L gamma V gamma is this smaller truncated shifted Yangian tensor differential operators on C star. So that this theorem here, and this functor provides us a relation. So AGV again was y lambda mu, and now on the right side here, I have y lambda mu plus alpha I. Tensor this thing, which is not very important. Yeah, so this is y lambda mu, and this guy here is y lambda mu plus alpha I. So I've now done my goal of constructing a functor between modules for these algebras, or between their category O's. And the theorem is that this does define a functor, which makes that diagram that I mentioned before commute. There's a functor. Making this diagram commute. Category O for y lambda mu. Category O y lambda mu plus alpha I. So this left guy is that long sequence I wrote down above, this restriction functor using this stuff. And then here I have the theorem from before, the equivalence with this KLRW algebra. Here I have the functor EI defined in this diagrammatic fashion. And here I have the same equivalence. So that we accomplished our goal of understanding this functor in some sort of geometric framework. Somehow the first geometric framework with this GA action, this Hamiltonian reduction, that would have been better, but it didn't seem to work. But so this is somehow, this other framework that I mentioned here is a not quite geometric framework, but a kind of Coulomb Branch framework anyway, for understanding this functor here. And I'll stop there. Thank you.
Okay, thank you very much. So questions, please. Elisa? No?
Actually, I did have a question. I wondered whether any of your results were prefigured in the physics literature. I mean, certainly Higgs branch and Coulomb branch are, that's terminology from physics.
Yeah, well, certainly the inspiration for the definition of this Coulomb branch comes from the physics literature. And well, one thing that certainly came from the physics literature is this, I mentioned this idea of generalizing this W lambda mu when mu is not dominant. And that definition, it has a non kind of Coulomb branch definition too. And that definitely came from the physics literature. As far as I know, nothing about these theorems that I mentioned here about the GA action, or this theorem about the this theorem here that about the relating these different Coulomb branches. As far as I have talked a bit with physicists about them. The physicists actually, well, maybe physicist is too strong a word, but like people like Tudor de Mafte and I don't know if he counts as a physicist or mathematician, but they are also interested in understanding, well, this, I would say, mirror dual of these Nakajima correspondences. And they have a kind of somewhat different way of thinking about it, and I don't know how their way of thinking about it is exactly related to what we're doing. I know in some special cases that their way of thinking about it is the same as our way, but in general, I don't know how their way of thinking about it is related to what we do.
Okay, thank you.
More questions?
Yes. So Joe, Yang asked you about if you choose the different eyes for the different simple roots question, but I would ask for the same one if you go at several steps of the simple root alpha I. So do you get the divided? Can you get the functor for the divided power of this E and F, or just to get the power?
No, that you can do. That's relatively straightforward. For example, in this language right here, you could take this, that would correspond somehow to splitting off a bigger factor than just C star, which would reduce the dimension of the ith GL. Like you want to change this GL VI, make it go down by more than one.
Yeah, that vi minus say more than 1.
Yeah, you can accomplish that by putting like something like this, by changing this guy here. And that does behave well, and you can use that to understand the divided power functor. Yes.
So that'll give the divided power functor, right?
Yeah. Yeah.
So that's very much similar to what Lustig was doing using the constructible shifts.
Yeah. Yeah. In a similar way, in the equivariety side, there's a sort of correspondence for the there's a sort of correspondence for the divided power too. Yeah.
Yeah. That's nice.
More questions?
I have a question. So in this toy case where we have cotangent bundles to Grassmannians, those correspondences also existent in the context of there also being cotangent bundles to partial flag varieties. So there is a bigger network of functors, of which those functors EI and FI are just special cases. Is there any such network around this T mu lambda modules?
Well, somehow in that, like in some sense, the reason why it happens in that special case that you can go from cotangent bundles Grassmannians to cotangent bundle of partial flag varieties is somehow because the cotangent bundle of Grassmannian is like a special case of a cotangent bundle of partial flag variety. So instead of thinking about SL2, you could have been thinking about SL3 or some other SLN. So you can kind of do the same thing in that way, but I don't know if there's something really more general.
Maybe in the okay, yeah, I'm not sure. Like GL infinity.
Yeah, I mean, you could try combine them all to some kind of GL infinity, and you can do that, I guess, probably in any of these settings, I think. Yeah.
Rina, are you happy with the answer?
Yeah, I'm happy, thank you.
Okay, more questions?
May I ask a question?
Sure.
Yeah. So I'm pretty familiar with the kind of geometric perspective in terms of G bundles on curves for getting the affine Schubert varieties, and having them associated with a co-weight via the pull condition. But I don't think I'm very familiar with the transverse slices and the modular or geometric description of what's going on there. Could you say a little bit about that?
Sure. So first of all, there's like a classic theorem of Grothendieck, I guess, which is that every vector bundle on P1.
The Birkhoff. Yeah. Okay, sorry, keep going.
Well, it has some different incarnations, but one incarnation you could say is that every vector bundle on P1 splits as a direct sum of line bundles. And in a similar way, every G bundle on P1, it can be reduced to the maximal torus. In that way, you can classify G bundles on P1 in terms of T bundles on P1, and T bundles on P1 are labeled by the co-weights. So from that, the isomorphism classes of G bundles on P1 is the co-weights mod the Val group. So, which is the same as the set of dominant co-weights. So this W mu consists of those G bundles of, let me just like write something, I guess. So if we have the affine Grassmannian, which is, you can think of as G bundles on P1 trivialized away from a point. And then if we mod out by this GT inverse here, well, this is modding out, oops, sorry.
Can you move it? Yeah, okay, good.
This is modding out by ways of changing the trivialization.
So a slightly related question then is that we have a uniformization theorem for an arbitrary curve where we can discuss the affine Grassmannian in terms of G-torsors on an arbitrary curve, but the Birkhoff decomposition is kind of tied to P1. Is that true?
Yeah, on an arbitrary curve, there's a similar statement where this with less useful statement, but this group would be replaced by the G of the. So we had an arbitrary curve.
G of the function or the
Yeah, we would have G of C minus whatever
C,
special
yeah, the
point.
puncture curve. Yeah, I see.
But well, it's a much like this guy is much smaller than this guy in general, which means this guy's much bigger than this guy, more interesting than this guy. And
Okay.
sort of usually this guy's pretty hard to understand, which is why this guy's hard to understand. But on P1, it's relatively straightforward, and so the orbits of this group on the affine Grassmannian are the same as this G bundles. And as I mentioned, this is the same as this co-weights.
Thank you. Thank you very much.
And then the slight thing, like what I mentioned, is that we don't really take this group, but rather we take this like G1 version of it, and that the effect of that is that it's remembering. You still remember some partial flag at infinity, so it's a little bit bigger. I mean, that's to get something that's really is transverse, because if you do this guy, these guys won't be have transversal orbits because they both contain G. So you have to go like this in order to make them really transverse to each other.
Thank you very much.
Welcome.
Yeah, okay. I also have a question. I don't know whether it kind of really makes sense. It's first it starts with algebra with truncated shifted Yangians, but it's not about Dinkin quivers. It's a story about which we wrote recently a paper with Rabchak, Yang and Zhao. So they appear in the following setting. We consider, I don't know how it's related to these transversal slices, but it's related to the derived category of coherent shifts on the resolved conifold, which is a Calabi-Yau threefold. And the space of stability structures there, it has a chamber structure. And basically what we did, we constructed for each chamber certain category of representations, actually of the shifted affine Yangian, but I believe there can be also a truncation as well. And so instead of the functors between these shifted by alpha I weights, like in your story, we have a functor which correspond to crossing the wall. Like, and well, in our case, there are infinitely many of them. And it's not really the Dinkin quiver story. It's the quiver, it's what is known as Klebanov-Witten quiver. You have two vertices and two arrows going in each direction. So 4 arrows altogether, 2 in one direction, 2 in the other one, and there are also relation. There is a degree for potential in the story. And there is this framed, like analog of the quiver varieties. There is a framing. There is a moduli space. In that case, it's sort of stable objects. And I mean, I see the analogy in these functors, which seems to go across the wall. And so I'm just wondering whether your story can be interpreted as having a stability structure.
Well, I have no idea, but I'll take a look at your I'll take a look at your paper. But you say the Yangian there is it's
shifted. Yeah, it's shifted affine, and it's not exactly your framework, but it's. I mean, it's rather related to this Nakajima Kadera. I mean, their presentation. But yeah, certainly it's related to the appendix of this paper of 5 authors, which you mentioned previously.
Okay. Interesting. I'll take a look. Thank you.
Yeah, all right. More questions? Well, if there are no more questions, well, Joel, thank you very much for very interesting and exciting talk. Thank you.
Maybe maybe I can come visit Kansas for real sometime.
Yeah, for that, again, we should open the border. Yeah, but of course, certainly you're welcome. I'm glad that
I seem to have a lot of friends there nowadays. So
yeah,
we're looking forward for you to be in Manhattan in person. I mean.
Okay, thank you. Bye-bye.
Bye, take care.